You can ask questions if you want, or I'm going to let you just sit there and ponder it for a moment. What do you see as the big difference between this and the problem before? I don't tell you what R of t is, right? I only give you a property of R of t, and that is that its magnitude is constant. That's the only thing you know, right? Okay. So think about it, and then I'll let people. Can you see it visual? Are you trying to visualize it here? Yeah, like we're in 3 dimensions, it's got to be, spherical, right? And this actually, because vector functions can be 4 or 5 or 6 dimensional, this is like even more abstract. But the thing is, how do you show it? You think you got something?
This is a constant that's always going to equal 0. Right?
Okay.
Since you multiply them together by the 0 vector, it's always going to be 0.
Wait, say it again?
When you dot product
Mm-hmm.
these two, since that's always going to be the 0 vector in every aspect, no matter how many dimensions, is going to be 0. So it's always
So R, the magnitude of the...
oh, I'm sorry, I didn't mean that.
So the magnitude of the derivative is a constant. You're saying that means... Sorry, no, the magnitude of the function is a constant. So you're saying that the magnitude of the derivative must be 0? Is that what you're saying?
Not sure.
You're kind of on the right track here.
I was thinking that was absolute value.
It is.
Yeah.
Yeah, it is.
forgot.
I mean, it's either way you want to look at it. What are you doing here? Because that's where you're kind of the closest to it.
To find out, to make sure,
Like-
they're orthogonal. If
Okay,
they equal
okay.
0.
I'm sorry. I see it, the prime. So you're
If it
okay.
equals 0, it's orthogonal, right?
Yeah. The only issue I have here is that you're saying that,
That. Oh,
okay, if you take out the absolute value there,
yeah.
then that means that would have to be the 0 vector, right? It couldn't be 0,
So it would have to equal that.
the 0 vector, right?
And then that would.
But is this being constant
Yeah.
enough for you to say,
Yeah.
just because the magnitude of the function is constant, can you then say that the derivative always has to be 0?
Right.
Right. But I think with enough time, I think you might actually get this one. Can I give you all a hint? Y'all want a hint? Do you have some? Let me give you a hint. What is that equal to? Magnitude of u squared, right? Okay. What do I want to show here? What do I want to show? I want to show what?
We showed that the dot product between the both. I'll use the what you read over there. Both the u vector or RT vectors are equal to 0.
You want to show that the derivative vector function dotted with the original vector function is 0. That's what you want to show, right?
Yes.
If you could show that that's true, you're done.
Yes.
Okay. What are you given in the problem?
You are
What is the only thing you're given?
You are given that the magnitude of RT equals a constant.
Okay. Right? Help me use this. Help me use this.
Wouldn't you be able to use the dot products of both vectors to say that equals the constant squared?
Okay, so square both sides of that equation.
Yes.
Okay, if I square both sides of this equation, what do I get?
The RT, the vector RT squared equals C squared, and that one.
Right? You agree with that?
Yeah.
Okay, now the left side is actually what? R of t dotted with R of t equals a constant squared, right? Now, that's not what I'm trying to show, right?
Yes.
But at this point, do something mechanically to this. I need to get an R with an R prime somehow dotted together. I need to somehow get that expression out of this expression. R of t equals C? No, no, we know because we don't know that the magnitude of it does.
You gotta take the derivative.
Take the derivative on both sides. Here we
That
go.
goes to 0.
So look, if you take the derivative on both sides of this, what do you get? What's a derivative of a dot product? So let me go back and just bring up the previous note. Where is it? Oh, the rules. Here they are. What did we say happens when you take a vector function, dot it with another vector function, and you take its derivative? You do the product rule, right?
Yes.
But we have the same function, don't we?
Yes.
So since I have the same function, doing the derivative now with respect to t on this side, and then the derivative with respect to t on this side, right? This will be r, I'll do it this way, r prime of t, what? Dotted with r of t, plus the same thing, r prime of t dotted with r of t must equal, now here's the critical part, it must equal the derivative of a constant squared, which is going to be 0. And now this is actually the same expression twice. So that's 2 of them, right? 2 of these r prime of t's dotted with r of t equals 0, right? And divide both sides by 2, and you have what you wanted to show, right? So next step would take you to here. So this is actually, I love this example because it gives you an idea, a glimpse into the way mathematicians have to think about things. It's not as mechanical, like do this, followed by this, by this. You're actually just, you got to work with what you're given, and you got to know where you're headed, and then you just got to try different things. So the key to this problem is squaring both sides so that you could utilize this property, and then recognizing that if you took the derivative, you would make what you needed appear. So pretty, is it easy to follow now that I've done it? Okay, all right. So I believe, now I would not give you, I don't think I would, well, I know I would not give you a problem like that on like an in-class test, because that I think does take some time to sit there and contemplate a little bit. But as far as like a take-home, maybe I'd challenge you with something like that. All right, 11, how are we doing here? Okay, let's just do one more note about the derivatives, because we'll come back and we'll start with integration next time. When you look at vector functions, when you have a curve in space, it's actually there's not a unique representation for every curve. In other words, I can create 2 different vector functions that draw me the same curve. So look at these 2. I've defined them down here. First one I'm calling R1 of t, here it is. This one's called R2 of t, here it is. And there's the graph of each of those 2-dimensional vector functions. And they draw the exact same thing. All right, you agree? Now, if I start the clock, so I start plugging in t's for both of these, I want you to just pay attention. These vectors right here are the tangent vectors, okay, the derivative vectors. Now, do you see what's happening? They're both drawing the same curve, right?
Right.
But that one's being drawn a lot faster than this one's being drawn, right? And So if you look at this curve as being the path of a particle through space, this particle is moving slower, which is why the vector, the derivative vector, is smaller, right? But this one over here is moving through space faster, and that's why its tangent vector is longer. All right, so two different functions drawing the same curve, but at different rates, and the derivatives are somehow showing us that difference. So again, there's a lot of information stored in these derivatives. We can compare them, at corresponding points on the curves. You can see the magnitude of this derivative is 8.06. That's how long that is. But over here, the length is 32.2. So somehow that length is telling us how fast, and that's what the next note is about. It says that if r of t is a vector function which represents the path of a particle or an object moving through space, then we will call r of t a position function. Now, if we take the derivative of that position function, we'll call it the velocity function. And the magnitude of that derivative function is the speed. So I think probably at this level, everyone knows there's a difference between speed and velocity, right? So velocity is both, it's like a vector. It has a magnitude and a direction, whereas speed is the length of that vector. So that's what this is saying. The magnitude of the derivative is the speed. And then further, the second derivative is going to give you acceleration, all right? All right, the larger the magnitude of the derivative, the faster the particle is moving at some point in time. All right, so there's, yeah, I think that's a good place. Yeah. All right, so I think it's 5:15. I think we can cut out, but let me show you something real quick. That's just real quick. I just thought about this. You can start packing up. I'm just curious if anyone has ever noticed this before. This is not profound in any stretch, but that's the basic function for a parabola, right?
Yeah.
Okay, so we learned somewhere in college algebra that this point right here is called the vertex, right? And we also know that there's a formula for this, yes? There's a vertex formula. I'm going to put it up here and see if it rings a bell. The vertex is this point HK. And the formula for that point is that h is equal to negative b over 2a, and k is equal to f of h. So if someone hands you a parabola, and they say, all right, you want to find that point, the vertex, all you have to do is be kind of like a monkey, and you just have to, like, whatever that is, you put there, make it negative, and then 2 times whatever that is. That'll give you the x coordinate. And then the y coordinate, you just plug that answer into the function. Does that look familiar? Have y'all ever thought about, or were y'all ever shown, or do y'all understand where it comes from?
Part of the quadratic formula, like where you have negative b on the top and 2a on the bottom.
It is related to the quadratic formula, right? That negative b over 2a, but there's another way you can come up with that formula. I was curious. I'm going to show it to you because it's super fast, super easy, and I think you'll appreciate it maybe. So right here, this is where the lowest point on a parabola is where the slope of the tangent line is 0, right? So just take the derivative of this. What's the derivative of this? What's f prime of x? 2a plus b, right? Okay, now I'd like to know where that's 0. Right, because that would tell me where the slope of the tangent line is 0. So if you set that to 0, I'm missing the x, sorry, I'm missing the x. 2ax plus b, set that to 0, right, and solve for x. And if you solve for x, you get negative b over 2a. So this formula for finding the h part of the vertex is just simply stuff you already did. Like you just set the quadratic equal to 0, right? I wonder if that would work for a third degree polynomial. So like what if this was to the third, this was squared, this was x, and this was plus d? Could we find these highest and lowest points? Well, we would have to just take this, set it equal to 0. But that would be a quadratic, so we maybe have 2 solutions. And what if this was fourth degree? Then we'd have to solve a third degree. So is there a formula for solving a quadratic? Yes, right? Quadratic formula, right? Is there a formula for solving third degree? Yes, there is. Okay. How about fourth degree? Do y'all know?
Yes.
There is. Fifth degree? Sixth, you think there's one for every degree? Nope. There's not. There's not. Unfortunately, it stops at 4, and it can be proven. It's not that we haven't found the one for 5. It can be proven mathematically that they do not exist for 5 and higher. All right, so we only get formulas up to fourth degree, and then after that, how do we do it? Some numerical way. We either have to use some crazy rational zero test or Newton's method, use an algorithm in a computer. So, all right, I went off topic. Y'all get out of here. Wednesday, I guess if you're turning in that first exam, you can turn that in, and then we'll pick up where we left off. Have a good day.